Franklin once discovered that light and draw discharge can magnetize steel needles. In April 1820, there was an evening lecture. It instead demonstrated the magnetic effect of current when the platinum wire is energized. The small magnetic needle near the platinum wire swung. This inconspicuous phenomenon did not attract the attention of the audience, but Thurston was very excited. He conducted in-depth research for 3 months in 1820. He announced the experiment. Ørsted connected one end of the wire to the positive pole of battery. The wire was placed parallel to north-south direction, above the compass needle. When the other end of the wire was connected to the negative pole, the compass needle immediately pointed east-west. He put glass plates, wooden pieces, stones, and other non-magnetic substances inserted between the wire and the overhand, and even the compass needle was immersed in a copper box filled with water. The compass needle still deflected, indicating that current can also create a magnetic field. This phenomenon is called the magnetic effect of current. The magnetic field of electrified straight conductor. The magnetic field around the electrified straight conductor is concentric circles centered on the position of the wire. The closer the concentric circles are to the wire, the greater the magnetic induction intensity. The denser the magnetic induction lines are, the farther away from the wire. The smaller the magnetic induction intensity, the denser the magnetic induction lines are. The direction of the magnetic field of a conductor. Hold the conductor with your right hand, and the thumb points in the direction of the current. The direction of the forefingers is the direction of the magnetic field. Second, the magnetic field of a solenoid. First, the external magnetic field of a solenoid is the same as that of a bar magnet. Second, the MPR rule. Hold the solenoid with your right hand. Bend the forefingers towards the direction of current. The end pointed by the thumb is the north pole of the solenoid. Third, the polarity at both ends of the solenoid is related to the direction of current in the solenoid. Fourth, how can we enhance the magnetic field of the current? Experiments prove that the strength of the magnetic field of the solenoid is proportional to the current and turns of the coil. Electromagnetism is caused by the directional movement of free electrons. Therefore, the strength of the magnetic field of a conductor depends on first the current magnitude. The greater the current in the conductor, the stronger the magnetism. The current increases, the stronger the magnetism. Second, turns of the coil. When the current in the energized wire is constant, the more turns, the stronger the magnetism. The more turns, the stronger the magnetism. The magnetic pole direction of a conductor is related to the current. An electromagnet crane uses the electromagnetic principle to lift and transport steel objects. The main part of an electromagnetic crane is an iron block. When the current is turned on, the electromagnet attracts the steel objects firmly and transfers them to the designated place. Cut off the current, magnetic disappears and the steel objects are put down. An electromagnetic crane can generate strong magnetic field force. It can lift dozens of tons of iron plates, wires and nails, waste iron and other various iron materials, without packing or bundling or tied. Can be easily collected and transported. It not only saves labor but also simplifies the work. When the crane is working, as long as the current in the electromagnet coil still exists, the lifted heavy object will not fall. The invisible magnetism is more reliable than a strong chain. In this class, we learned that current can also create a magnetic field. This phenomenon is called electromagnetic magnetic effect. After class, please think about: can a magnetic field generate an electric current?